back. All right, hello everyone. Good evening. I'm taking a break from my 90s R&B session to make this quick YouTube video so we can all practice for our Simple Machines test, the final, which is coming up. Got to do good on this test. Going to be super important. So anyways, what I'm going to do is we're going to go over 3 machines tonight: the lever, the inclined plane, the wheel and axle. I'm going to do one problem from each of the sets, and then there's a couple more for you to try on your own. Okay, so here we go. For each one of these, we're going to do the following. Let me go back here and let's do a quick notes session while we're at it. The IMA, that is the ideal mechanical advantage. That's what we calculate the mechanical advantage to be, what it's supposed to be. And that is theoretical, so it only exists in sort of our theoretical world. It doesn't actually exist in the real world. That is done by dE over dr. That is the same for every machine, right? You just have to find the distance effort, the effort distance, the resistance distance, divide them, and you're going to be able to find your IMA. Your AMA stands for the actual mechanical advantage. So this is like when you test it in real life and you see like what's the actual mechanical advantage after we lose stuff to friction, after we lose efficiencies to all these different things. That is so that deals with the actual measured forces. You remember measuring things with the force sensor. So it is FR over FE. Note that these two are switched, right? It's the resistance force divided by the effort force. Okay, onward and forward. Our first simple machine is going to be a lever. Okay, so the first problem is a 10 Newton weight is hung on the short side of a lever. Okay, so I'm going to just note some things that are kind of important. Let's see, with blue, we'll just draw a box. Okay, it's a lever. We have a 10 Newton weight. I'm going to note that as being my FR, my resistance force, because that's what's going to sort of work. That's what I'm trying to lift, right? And that's what I'm trying to do. I'm trying to lift a 10 Newton weight. And then let's see, I have my short side is, so the force sensor is placed on the longer side. The 10 Newton weight is hung on the short side. So the short side is 5 centimeters long. That is where the weight is held. So that must be my dr, right? The FR is 10 newtons, and it's hung on the short side. The short side is 5 centimeters. The long side is 8 centimeters. That is going to be my dE. So that might help me a little bit here. Let's draw a quick picture. We'll put our fulcrum in there. This is probably going to be tough to see. Okay, there's the short side right there. So we'll put our hanging thing. What is it? 10 newtons and a distance right there of 5. You could see my really crummy dimension line here. Okay, so we'll put in our other dimension line here. That one is 8, and then right here is our unknown FE. Okay, so calculate the IMA. IMA equals dE. Sorry, that looks a little bit more like a P over dr. I'm not so great at writing on the tablet yet. dE is 8 centimeters. dr is 5. So the IMA is 8 over 5, or we could say 1.6. Is that right? You guys could double check for me. 1.6. Okay. And then it says the force sensor reads 7.85 newtons. What is the AMA? Okay, so we know what our FR is, and now it's saying our force sensor reads that. So that must be our actual effort force. Okay, so we're going to do 10 divided by 7.85. Pardon me while I type this into the calculator. It's a little bit too late to be doing a lot of mental math. 10 divided by 7.85. 7.85. That's going to be 1 equals, and I'm going to round it here to the nearest tenth. Let's do 1.3. And then let me double check while I got the calculator right here. Let's do 8 divided by 5. 8 divided by 5. Make sure that is actually 1.6. It is. Okay, my mental math held up there. Thank goodness. All right, so now we're going to do our efficiency. Now, the efficiency is where we're testing. We would expect in most situations the IMA to be bigger than the AMA. And then we want to see what percent efficiency we actually have. So the formula is, let's see, what is it? It's AMA divided by IMA times 100%, right? So, or times 100, and then we make it a percentage, right? So let's just do this. Let's just say 1.6, or sorry, pardon me, 1.3 divided by 1.6. And then what does that equal? 1.3 divided by 1.6 and equals 0.8125. So I'm going to round that to 0.81, which equals 81%. Hopefully that all makes sense. Okay, so that's levers. Pay attention to this picture right here and kind of what we're doing there with the levers. Okay, so levers are relatively easy to understand. Well, they're not that easy. Anyways, we'll move on. I'm talking. An inclined plane. All right, inclined plane 1. An inclined plane has a slope of 1 to 10. It rises to a height of 2 feet. So remember from algebra, our slope ratio, let's switch to black for this one, is rise over run. So let's draw a quick picture here of our ramp. Now it's got a 1 to 10 slope, so it's going to look something like that. This is going to be, let's see, it has a slope. It rises to a height of 2 feet. So that goes up 2 feet. Then this must be necessarily 20 feet. And then I don't know what this is right here, and that's important to note. X equals, okay? So we're going to have to figure that out using the Pythagorean theorem. So I'm going to use a squared plus b squared. I'm going to make that a squared. That's going to be, the 20 is going to be b squared, and we're going to figure out c squared. So I'm going to have 2 squared plus plus 20 squared equals c squared. And then I'm going to combine a couple steps. I hope that's okay with everyone. So 2 squared is going to be 4. 20 squared is going to be 400. So we're going to have 404 equals c squared. Then we're going to take the square root of 400, and it's probably going to be very close to 20. So let's see, square root of not 2, but of 404, 404. And that is 20.1. Okay, so now it's very important to note that when we have an inclined plane, the DE is the distance of the longest side, right? It's this inclined plane distance right here. This is our DE, okay? This right here is our DR, okay? So the height is the DR, and the distance that it actually travels along the hypotenuse of the triangle there, that's our DE. Okay, so DE over DR, DE divided by DR is going to equal 20.1 divided by 2. It's going to be 10.1 if I round. Equals 10.1 right there. That's the IMA. Okay, and then how much force would you expect to use to bring up a 40 Newton cart? So now this is where things kind of get hard, right? Because, well, let's do this. Let's scroll down a little bit. How much would you expect to use to bring up a 40 Newton cart? So how much would we expect to use? Well, we would expect things to be perfect. Well, we wouldn't expect them to be perfect, but we're going to have to assume that it's 100% efficient for this question because we don't know what the efficiency is. It doesn't actually tell us what the efficiency is. So we're going to expect to get all 10.1 of our mechanical advantage, and that's how it's going to be, right? So actually in this case, our IMA is going to equal our AMA. Those are going to be equal in this case. So AMA equals, let's see, what does AMA equals? It equals FR divided by FE, and FR is in this case 40 newtons, and FE, sorry, that's really bad, FE, you know what, let's do it down here. FR over FE equals 40 over let's see, equals 40 over I don't know, it just equals our FR over FE, over FE, we don't know our FE yet, but we do know what our AMA is because it's equal to our IMA, so it's going to equal 10.1 over 1. Okay, so now we're going to use our cross multiplication technique, and we're going to say 40 equals 10.1 times FE. Hopefully that was readable right there, so we're just going to simply divide both sides by 10.1, divide by 10.1. That'll cancel out. Let's see what 40 divided by 10.1 is. 40 divided by 10.1 equals 3.96. I'm going to have to round it to exactly 4.0. 4.0 newtons, right? So you can kind of see we're getting that 10 to 1, or that we're getting that 10.1 mechanical advantage, right? A 40 Newton cart only takes 4 newtons of force to push it up there, but we have to push it 20 feet instead of going up 2 feet, right? So much lower force, much longer distance. That's what that's what mechanical advantage is all about, right? You trade either distance for force or force for distance. Okay, moving on to our last one. We got a couple of inclined planes here. Wheel and axle 1, right here. Okay, so wheel and axle, perhaps the hardest to visualize and to calculate, but well, the calculations are still the same, so it's really not any harder to calculate. It's just kind of hard to know exactly what's going on there. All right, so let's read the problem here. In a well crank, the handle is attached to a 2-inch radius axle. Okay, so let's see. Let's do some highlighting here. We'll grab our green. So we have a 2-inch radius axle. The turning circumference of the crank wheel is 16 inches. Okay. And find the circumference of the axle, or the radius of the wheel. Okay. So we got to, first thing we got to do is let's draw a picture of the system, figure out what's going on here. So we have this like crank on here to pull things out. So there is our crank. Let's see. Let's switch to a more readable color. There's our crank right there. I don't know how to draw this, right? And then that's attached. So we got our handle right here. Put my fingers on that, my thumb, all the essentials. Here we go. So then this is attached over here to this little axle right here, which has a 2-inch radius. Okay, so I'm going to note that right there. 2-inch radius. Okay, and then we don't know, we just know that the handle of the crank is 16-inch circumference. So we're going to do this. We're going to do 16 divided by pi, and then we're going to divide that by 2. Okay, so we're going to do 16 divided by pi, 3.14. That equals divided by 2. Okay, so the handle crank is actually has a 2.5 inch radius. 2.5 inch radius. So I just took the circumference, turned it into a radius by dividing by pi, then dividing by 2. Okay, so it asks for what is the IMA of the system. So we're just going to simply take our DE, right? DE, the effort distance is obviously, the effort is going to come from the human, of course, over DR. Oops, not RD, DR. So the handle is 2.5 and the DR is 2. We're going to divide 2.5 divided by 2, and we're going to get about 1.3 for our IMA. And then it says how much force is required to lift a bucket of water weighing 40 pounds. Hint, this is the ideal effort force, not the actual effort force. So again here, IMA equals AMA. So we're going to assume our IMA to be equal to our AMA. 1.3 equals FR over FE. Now these always take a little more space than I really planned for, especially with my sloppy writing here. So we have 1.3 equals, and then FR is going to be 40 pounds, and we don't know what FE is. We're searching for that. We're looking for that. Okay, so we're going to do cross multiplication, and we're going to get 1.3 FE equals 40, and we'll divide by 1.3, divide by 1.3, cancel those out, get FE is equal to 40 divided by 1.3, and we'll get it equals 30.1 pounds. So you could see the ideal mechanical advantage is not huge here, so we don't get a big reduction in the force, right? So we're going to FE equals, and we're just going to leave this one in pounds again. We're going to say 30.1 lbs pounds. All right, so there you go. That's all the examples I'm going to give you. This is probably a long